This is a walkthrough of Problem 2 on Exam 1 of Module 7 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a wheelbarrow with 100 kilograms of decorative stone in it. The center of mass of the stone is 15 inches behind the wheel and 20 inches in front of the legs. The horizontal distance between the handles and the wheel is 4.5 feet. What is the normal force on the legs of the wheelbarrow from the ground? Part B, what is the force needed to lift the wheelbarrow using the handles so that the legs are off the ground? As always, we better start with a good diagram. There's our wheelbarrow. There's the stone. The center of mass of the stone is 15 inches behind the wheel. There it is. And 20 inches in front of the legs. There it is. And the handle is 4.5 feet from the wheel. Okay. Now let's put in the forces. We have the stone pushing down on the wheelbarrow with the force of 1,000 newtons. We have the ground pushing up on the wheel with some normal force. We have the ground pushing up on the legs with some normal force. Remember, the wheelbarrow is just sitting there. Nobody's trying to lift it yet. So those are our three forces. I don't see a mass of the wheelbarrow, so it looks like we're ignoring that, which is not that bad of an assumption when you consider how heavy the stone is. So with this assumption, these two must balance the 1,000 newtons of gravity. Let's take torques about the point at which the wheel contacts the ground, because we don't care about this. It's asking for this force. Take torques about here. We have gravity, which we know, and there's one equation, one unknown. Gravity exerts a clockwise torque, right? Tick, 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 goes this way, spinning about this point. The distance is 15 inches, it says right there. The force is 1,000 newtons, mg. mg times the distance is 15,000 newtons inches of clockwise torque around that point. Counterclockwise torque is from the normal force from the legs. It's 35 inches away, 20 plus 15, and that's the force, that's the distance. We can set these torques equal. There's the clockwise torque, there's the counterclockwise torque. We have one unknown because we judiciously chose our point of rotation. Divide both sides by 35 inches and we get 430 newtons for that force, which makes this 570, right? Because they have to add 1,000. Question didn't ask for it, but we'll get it anyway. Part B, we need to determine the force needed on the handles to lift the legs off the ground. If the legs are off the ground, there's no more normal force. It's a contact force, right? So we got to get rid of this force, take this force away, and put a force over here. Somebody's lifting on the handles. There it is, 4.5 feet away. Now we can take torques about the same point right here. The gravitational torque didn't change. It's the same distance away. It's the same magnitude. The clockwise torque from gravity is still 15,000 newtons inches. Now this lift force is further away. It's 54 inches away. We have to convert feet to inches because this torque is in newtons inches. So we have this lift force times 54 inches. Setting this equal to the clockwise torque, we can divide by 54 inches and get the lift. And that is 280 newtons, and that's the answer to problem 2.